I'm going to talk a little bit about some abstract problems, particular solutions, some open source software, and try to blend them all together, but in the DP and TEE space. And for those of you who have been here for the day, we've seen I can piggyback on great talks, but or if you're witnessing this as a recording later on, go back and see Mike Bursell's talk from CCC about the ability of TEEs. Zhao Li's introduction to differential privacy in his particular use case. I'm gonna piggyback off their excellent efforts. What I'm interested in is to talk about um, causal learning. Um, that, in my mind, is a sort of basic building block of how we learn things, how we do science, how we solve problems. Causal learning, predictive learning are similar, but causality has to have, it's not just what do I think is going to happen tomorrow, but are there things that I can influence in the world to change what might come about if I'm able to manipulate them? Why is this interesting? I said I was going to talk about abstract problems, and now I have a graph that is about ad revenue. Um, at its heart, causal inference is a big part of what makes the digital ecosystem work. Um, Digital ad revenue, as you sort of see in this graph, has over the last 10 years has come to dwarf traditional ad revenue. Traditional ad revenue is not going away, but this is the story we know that the internet is powered and fueled and has this engine of being able to direct ads in ways that are meaningful to users. And that market has really grown, but we also know that that market has been dominated by a few players that are, we sometimes talk of the walled gardens, the Metas, the Googles, increasingly the Amazons, who have their own ecosystems of information and can do everything on their own. Um, and trying to open up this engine for the open web is part of the mission of Mozilla, is part of the work that I do, and is sort of this underlying interesting question. So I'm just going to talk briefly about what's the fundamental problem that we're trying to solve, connect it to basic problems of scientific inference, and then talk about how TEEs and differential privacy play one role in that solution. So let's say I want to serve an ad, but I'm not Facebook Blue. Um, so I'm a small open web player. I release a newspaper, and I am serving ads to individuals. And some advertiser out there wants to pay me to show those ads. And we have two different pieces of information. If I'm a statistician, I think of them as the outcome variable and the independent variable. The platform knows who they showed advertisements to. The advertiser knows who bought a good from them. Say the conversion, the thing that they're trying to do. It might be sign up to an email list or put something in a cart or whatever it is that they're trying to generate. And we can't learn the effectiveness of that ad on that conversion event unless we bring the data together. Okay. Um, and then we can run some sort of joint computation. And if we want to do this in a causal way and not just in a predictive way, the advertiser themselves maybe can run an experiment where they randomize at the point that they're about to show an ad. They might randomize whether they show the ad or not, and then they look at what's the causal effect of the effect of the ad on the treatment group, the people who did see the ad compared to the people who did not. Okay. I've used this ad ecosystem to explain this because this is a really important central piece of modern technology and modern um, driving a lot of social good on the open web. But these things that we're constructing are very, very similar to all sorts of other kinds of problems that people try to run off the same kind of data. So I could have, couched all of these terms in terms of clinical trials, and we had one use case earlier that sort of said something very, very similar, where instead of the causal effect of an ad, I'm interested in the causal effect of a particular treatment pattern. And again, when you're solving interesting, difficult behavioral problems, It's often the case that two parties have a split of the data. The practitioner might know which clinical trial you were assigned to. You might know your initial course of treatment early on in the disease, but it's some other party like your general practitioner who 10 years later on is measuring what's the actual long-term effect on your course of life. Your long-term health outcome might be divorced from your randomized trial participation. We've seen some fantastic work coming out of people like Raj Shetty publishing in Nature, talking about how do you lift children out of poverty. And there, you have what neighborhood did you grow up in is incredibly sensitive data that you learn from the U.S. Census. What was the trajectory of your career attainment is held by the IRS. That data can't be joined, but we want to run sort of these joint causal estimates to say, are there interventions that we can stage early on in childhood to bring children out of poverty? So again, it's this basic building block of inference that when we have private behavioral data, how are we going to learn what the causal effects are and sort of reach social goods? And why does this? First of all, why do we need to think about privacy in this domain at all? Why isn't it that we can't just sort of throw all this data together, trust a party to run the execution, and then release the answer and say, look, this is the answer we constructed. What we've learned over the last decade, particularly some pioneering work by the U.S. Census Bureau, who's very worried about this question, is these seemingly simple answers, like what's the causal effect of early childhood spending on educational attainment or long-term income? When you start to just split the data in innocuous ways by gender, by geography, by other kinds of things, um, very, very quickly you're starting to leak individual information about individuals who belong to unique combinations of those cells. And so the US Census Bureau showed that when they were producing very, very seemingly innocuous, very genuine, non-malicious tables of summary statistics on the US Census, when they plugged that into off-the-wall SAT solvers, they could reconstruct 30 to 40% of the underlying data that was sitting in the US Census Bureau. So they moved to building a system where every answer that's being generated, all the tables of statistics that the US Census is releasing in the decennial, is being done with differential privacy to give this gold standard guard that that's not going to happen. Okay, so how do we build that into these kinds of models? What typically happens, to the extent that there's any way to understand what the causal effect of an ad is, which is how we measure, which is how an advertiser might decide, should I send my money to, should I send my ad revenue to Google or to Meta, or can I send it to a local newspaper, is that they send all of their conversion events to the platform. And so the platform can construct a data lake and run that and say, trust me. But obviously, we don't want to be sending our data to everybody, and we probably even shouldn't be sending the data in the clear to the largest platforms. That's a giant privacy violation and allow the platform to build a profile of the individual. So instead, what everybody here is going to nod at very easily is to say, how do we build something where that computation exists inside some sort of pet solution? How do we compute the quantities of interest that we really want to know, which ads are working, which demographics are providing conversions, which platforms we should be sending ad revenue to, so that everybody can compete on an even playing surface. We're going to do something here that has a pets-based solution to sort of open up advertising on the open web. Allow the kinds of things that allow an advertiser to spread their ad revenue across different sites on the open web. Okay, so what does that normally involve? There's going to be some combination, like we've seen in so many solutions this afternoon, some combination of pets that creates an end-to-end solution. I started off as a research scientist at Harvard, and I still have a foot there, and I'll talk about that later. But in academia, it's very, very common that you specialize in one thing. And if I focus on differential privacy, I go to the differential privacy conferences and I talk about differential privacy problems. And I know who the people down the hall are who do MPC or TEEs. And we might share a beer, but we don't necessarily understand each other's problems. I love these kinds of events, and I'm really, really thankful that these are the settings in which we get to stitch together solutions in ways that are sort of innovative and bring around end-to-end solutions. First off, we need to make a join. We need to understand what data do we have in common that we might be able to compute on. So some form of private set intersection. We've seen that turning up in a number of systems here. Lots of possible choices there. Maybe that's an FHE solution. Maybe that's some sort of hash or encryption. Then after that, once we have the data, once we understand which data we hold in common, and we can run a computation on like what is the causal effect of the random treatment, we're going to now run some sort of privacy preserving compute on that data. So that might be in a TEE. We might maybe we have the compute power or the small scale to be able to run that in MPC. Maybe there's a way if it's only pluses and minuses or something like that to try to guarantee that within FHE. Clean rooms are out there. Uh, I hear nobody laughing when I say clean room, but most of you are probably on mute. Um, and then at the end of this, oops, it's my PDF is a little corrupted. Then we finally, we have an answer, but again, we don't want to release that answer in the private, just into the wild, because if we start releasing multiple answers, we're going to be leaking individual level information about the people who are unique that could be creating those answers. There it is. So this combination, and there are different systems out there, in the last 5 years, emerging in the ad tech space to sort of stitch together different paths through pets to do this. I originally worked at Meta working on these problems, and one of the first systems that they devised and that they've been public about is a private lift. And that's a really high power compute intensive solution where first it's FHE for the join, then it's MPC for the compute, then it's DP possibly on the output. So that's one path through there that gives you, okay, now we do not need to share that data. The platform and the advertiser are not going to learn, first of all, who they have in common. They're not going to learn the conversion behavior of the advertiser's not going to learn the conversion behavior. Or rather, the platform isn't. The advertiser's not going to learn who got shown in ads. And we're going to have that guarantee if we have differential privacy at the end of this. After working for Meta, I want to talk about a system that we've devised at Anonym, which has now been now 1 year ago acquired by Mozilla, where we have a service for ad tech platforms, for advertiser platforms, to do this, but with a different combination of pets. Okay, so first do hash of PIIs and do that join inside a TEE. So heavily leverage the TEE expertise here. So much faster, so much easier to compute in. Run the computation on the join via the hashed PII information. So using the TEE to preserve the compute, and then embed the DP code inside the TEE to give output privacy. So that's a particular solution. There's a lot of people here from TikTok, and if you, for example, you want to run this solution using Mozilla Anonym's technology on your Lyft campaign in TikTok, then this is live and this is public. This is a way that an advertiser can privately compute the effectiveness of an ad campaign on TikTok without having to share any of their data, or leak any of their data, or vice versa, learning anything about impression behavior at TikTok that they didn't already know. There's a lot more that we can talk about in these systems. Obviously, a lot of people have talked about attestation in the TEE as being another form of the security model here that we know exactly what code was run. I want to focus on at that end stage, the differential privacy. So we've had a few reviews about differential privacy. Differential privacy is this mathematical gold standard guarantee. It's a definition. It's not an algorithm, right? That says an algorithm is differentially private if we can make a guarantee that if we have a data set and we're releasing answers out to analysts, and maybe we worry those analysts might be malicious, they might be an adversary, that if there are answers coming back to that adversary and the adversary cannot distinguish from those answers whether, say, an observation in the data set is changed, its values, or maybe even disappears entirely. If the adversary is completely blind, it's cryptographically indistinguishable which of these data sets that answer came from, then that answer is differentially private. And it gives us this strong guarantee to an individual. Well, should I be worried about my data going into this data set? Well, look, your data can be in there. Your data cannot be in there. You can lie about your answers. It's not going to change what the adversary sees or learns about you. So you have this strong guarantee that if there is some value to you of your data joining the data set, you shouldn't worry about joining the clinical trial or having your data studied by the Ross Chettys of the world. Uh, and so, again, it's a definition, not an algorithm. And then the question is, how do we build algorithms to create these causal estimates that obey the differential privacy algorithm? And this is a basic building block of differential privacy as to how do you compute a mean? Lots of causal estimates are really just about means and differences of means, or what was the mean effect when you were given treatment compared to the mean effect when you were in the control group. So for differential privacy, when we're thinking about a mean, this is sort of a takeaway point. We want to say we want to add just enough high precision tailored noise to drown out the signal that one individual could make to the signal, the contribution they could make to the mean if their data changed in the worst possible way. And the worst possible way here, the most dramatic possible effect they could have on that estimate is to go maybe from the minimum bound to the maximum bound. So if I move somebody from the lowest possible value to the highest possible value, it's going to slightly move up the mean. It's going to move up the mean by that range divided by n, and I'm going to add just enough noise to drown that out so that I have a guarantee that I'm not going to learn anything about me. That's a basic building block of DP. At some level, that's really simple. And causal estimation is just a bunch of convoluted means, but there are lots of ways to sort of improve and bespoke tune that to the ad case, tech case. So, for example, we want to think about not just moving across the range of the data, but maybe what also happens when we switch users between treatment status and think about a much more slightly complicated setting. What happens if they move across treatment status? What happens if they also move across their feature domain? Yeah, what happens if they, change which device they're logging in on? It makes the calculation slightly more complicated, but the essential sort of idea is there. And so, one thing that we've been doing to build this out is highly tuning the algorithms that exist for differentially private causal estimates to leverage all the things we know about causal estimates. So, first of all, you don't just want an estimate of the mean; you want to know its uncertainty so that you can make confident statistical predictions. So, what are good algorithms for standard deviations as well as means? There are clever ways that we've been working on to get lower levels of noise with exactly the same privacy guarantee by thinking about individuals who are not worst case and understanding how we can leverage their information a little bit stronger than is typically done in DP and means. Often in these settings, we don't know what the natural range of the data is, particularly if these are like conversion values or a number of events that's unbounded. So DP algorithms for clipping the bounds automatically. And then just how do you do statistical inference inside DP? Like how do you get t-tests that reflect both the uncertainty of sampling and the uncertainty that's coming about through differential privacy? These are all things that go into making a highly performant differentially private algorithm that solves this use case. If that sounds hard, sometimes it is. But also, I want to put in a pitch here for another project that I work on, which is OpenDP. So thanks, as we're shouting out to people, thanks to Ming Shen earlier who mentioned OpenDP and our community meetings. OpenDP is a library where we are trying to bring together sort of highly vetted, trustworthy components for stitching together differentially private algorithms. I think one of the things that we learn about crypto in the preceding 2 decades is really nobody should roll their own crypto. Right? You want to use the crypto that everybody else is using because it's trustworthy, because everybody's eyes have been on it, because everybody knows what everybody else is doing, because there aren't going to be these exploits that nobody knows about. So similarly with differential privacy, you want to use some of the fundamental ideas are really, really simple, but then getting them to actually work in a real system where you need to make sure your randomness is cryptographically secure. You need to think about the differences between a theorem that's been proved in the space of real numbers and an algorithm that's being computed on finite floats. There are all these sort of side channels and leverages and timing attacks. You want to have a library that sort of does that for you rather than spend the 6 months to build one Gaussian mechanism that takes account of all of that, and maybe you get it wrong. So the goal of OpenDP is brings together the community of researchers, brings together the community of practitioners, also the stakeholders who are trying to protect private data, get them in one place, get them to understand like what does the community need to be doing to build good systems, and also build out a library that we can all sort of trust and build off of. So DP is both a community. OpenDP is both a community of stakeholders and practitioners and researchers where we sort of advocate for privacy, and particular differential privacy, and think about what are the problems that will make DP practical, as well as a library that a number of people have committed um, to sort of create sort of that reference code base that you can use and trust and is trustworthy. As Here's a snapshot that we saw earlier in Ming Shen's graph. There are community meetings for OpenDP. I encourage people to come to the community meetings for OpenDP. The next one is in Dublin. So, I mean, who doesn't want to go to Ireland in September? Last year, Wan Rongzhang, Bojan, both from TikTok, were there giving presentations. Encourage anybody who wants to talk about not just things they're doing in OpenDP, but things they're doing in the DP space to come to the community meeting, and particularly practitioners. Um, it's a very diverse community. We have a very large number of working groups that are thinking about sort of policy and practitioner topics like how do you construct good privacy attacks? How do we open up information about the ways that our differentially private systems are being built? Like how are we building like registries of deployments, and what are the responsible ways to be using DP, and making sure that we're not privacy washing, but that we're actually providing good privacy standards and educating regulators to make the right questions about systems that are claiming the DP umbrella. There's summer programs if you've got students that are interested in working with us for a summer. OpenDP.org, take a look if this is interesting to you, or reach out to me for questions. As a conclusion, uh, in the ad tech space, one more time, end-to-end solutions have to involve a variety of pets. There are different ways to stitch them together to get to final solutions. I think that for platforms that have limited resources, the combination of differential privacy on top of TEEs is a very, very practical balance between compute cost and a high level of threat guarantee. Um, Opening up these kinds of systems means that it's not just the walled gardens who have access to privacy preserving computation for ads measurement and ads delivery, but that all of the small players in the open web can show that what they're, and medium players as well, can show the effectiveness of their users and the engagement that they can get from putting ads against their content, and keep them afloat in this world. And that pets, is at this level of maturity now where it's no longer we say, oh, we have to just, allow the data to be sucked up in non-privacy preserving ways because we don't have alternatives. There are real solutions now for sort of a privacy forward open web that has meaningful engagement with users, and is not sort of a threat to constantly uncovering user behavior and constantly building scary profiles of users. Um, Thank you for your time on this. And if there are questions, right away, I'm happy to answer them. If there are questions that occur to you tomorrow and the day after, please reach out.